All right, I am Michael Kubacki. I'm here from Microsoft to talk about work that we've been doing to write UEFI code in Rust. So I'm in the core UEFI team at Microsoft. We are in the core OS organization. We work with first-party teams within Microsoft, but we're very ecosystem focused as well. So I'm also a Tiano Core or a steward in the Tiano Core organization. We work with EDK2 and a lot of upstream projects in order to work out firmware work that needs to be done into those projects. Today I'll be talking about the work we've done in Rust and where it's currently at and what we need to do next. So the agendas, we'll talk about memory safety, we'll go into Rust in firmware, what that means, and then we'll go into the project that we've developed called Patina. I think the main thing to take away from my presentation is to think about writing firmware more safely. So it's not necessarily, what we're trying to do is think about modernizing the way that we write firmware. The binarily presentation before me was very fortuitous to have because it kind of outlines some of the problems that we have with memory safety in firmware and also memory mitigations. And so I think if you take something away from this presentation, it'll hopefully be that we can do better for memory safety and firmware. We can think about the way that we write firmware a little differently to do it safer. And there are facilities in place to do that. I think whenever you look at a presentation like the one yesterday in Go and what's happening there with memory safety, we're really looking at the way to most effectively solve a problem. So it's not necessarily, do you write the language in Go versus Rust? It's understanding what the problem is and the most effective way to be able to solve that problem. And that's what I'm going to show you today, what our problem is that we're trying to solve and how we solve that. So hopefully you understand why we are doing what we're doing. So firmware has always evolved over time. We started with legacy BIOS, and as complexity has increased in systems, we've revised the way that we write code in order to adjust to that complexity. The UEFI standard is one way that we did that in order to define standardized interfaces and ways to communicate between the operating system and the firmware. As the implementation for that followed, we got Tiano Core, and then we went into segment scaling, right? Where we scaled this solution across different segments. Where we believe we're at now is we have this proliferation of memory safe languages and focus on safety. We're beginning to see that as operating systems become more hardened, people are beginning to look more at firmware as an attack vector into the system. And so we need to think about not only the way that we apply memory mitigations like stack guard, heap guard, NX protections, but we also need to think about the way that we write firmware so it's designed to be safe. And that's kind of the emphasis of this work. This is showing the number of firmware-related vulnerabilities in National Vulnerability Database. As you can see, it increases over time. And that kind of plays into the fact that as it gets more difficult to attack a system in other places and more protections get put into place, people start to look at lower levels like firmware in order to do that. This kind of builds on a presentation at PlugFest 2020 that was given on Rust. In that presentation, it outlined that there are a lot of memory safety related issues in EDK2 specifically, but also in firmware. And this gives some of the breakdown of the percentage of issues that fall into different categories, like a buffer overflow, integer overflow, and where some of the security issues originated from in terms of the category of issue. In that presentation, they highlighted that Rust can help to mitigate some of those issues and that we should start writing critical firmware modules in Rust. And that was in 2020, so 5 years ago, and at the time we started looking at Rust, and there's a lot of momentum picking up in the industry about it, and looking at, well, how do we most effectively take this language if we start with the fundamental problem that writing code in C is very, very error prone, and we obviously have problems with it. Our unit test coverage in EDK2 is at 1%, right? We're not testing code, we're writing it in a language that's prone to problems. Where do we go from here in terms of leveraging the languages available to most effectively solve this problem? And so that work was interesting, but like a lot of early work, that focused on writing applications in a memory-safe language. For example, a boot manager, a network application, a diagnostic application, or whatever, some crypto service. At the end of the day, the problem with that is that you're always calling down into C code. So unless you write the fundamental underlying memory allocator, the memory dispatcher, and the low-level services in a pure memory-safe language, it doesn't do much to build that top layer on top. It's helpful. It lets you know that that top layer is safe and it's probably better than some of its peers. But at the end of the day, you're still calling down into code that has the issues I mentioned in the other slide. So we looked at Rust. It was interesting because it's used in a lot of applications from command line, WebAssembly to embedded. We're not super religious about the language. We're just looking at an effective way to solve a problem. And Rust seemed to fit that well in terms of the zero cost abstractions, its performance, the reliability it brings to systems, and developers report being productive in the language once they start working into it. So it's all great reasons to dive in further and see what we can do with Rust and UEFI. Some of the initial benefits that we noted is Rust, at least with its safety checks performed during compilation, appears to be relatively lightweight. It puts more of the burden on the developer to think about how you write safe code. You don't just write code like in, let's say, Python, for example, where you're going to just use different memory and not really think about the way that you're using it. In Rust, because we are working at a low level, we need to think about that. It does matter if something's on the stack versus the heap. It does matter how large that is, and it does matter when it's accessible as it passes through different components during the boot process. So the memory safety without garbage collection became a big part of this, and having less overhead, the stringent type safety concurrency rules also was a nice advantage of Rust. And as we start to think about the overall effort that we're doing, which is really to modernize firmware development, with Rust being a part of that, not the primary focus, we can explore ways to write code that is faster and runs more concurrently, right? And doing it in a language that has the ability to do that more safely just makes sense as a starting point. Another big selling point of Rust is that we've typically been siloed as open source firmware communities, right? I think in this conference we got together as the OSFC, Plugfest, Core Boot, UEFI, and everyone goes off and we all have our reasons for writing firmware the way that we do. But at the end of the day, a lot of us want the same thing. We want performant, reliable firmware. We want it to be relatively small. We want it to be easy to understand and work with and use. And we look at this as an opportunity to break at least out of the EDK2 silo, which has its own custom build system and header files and way of doing things, and start to work with a broader set of developers that are not firmware developers, but they're Rust developers. So we can pull in Rust crates, we can share them with embedded operating systems, we can share them with other firmware projects, and we don't layer a bunch of opinionated, project-specific build logic and other stuff on top of it. And so one of our goals as we did this is to not go too far off the well-proven path of Rust and stay with mostly upstream tools and code. The other one is productivity. So coming from a C environment, we get generics and traits. Those are great to work with. They're just aspects of a modern programming language that make it easier and more fun to program than writing in C, and we can get more code reuse. We also get better tooling with built-in documentation. We don't have to go find Doxygen. We don't have to use Uncrustify to do our code formatting. We don't have to go use Coverity versus CodeQL for static analysis. We have all that built into the language, and a lot of the problems that those tools find, we're not even allowed to make, right? So whenever we go and we look at the 600 issues open in CodeQL on the C code, and people are not checking a null pointer, they're doing this, that's not even allowed in Rust. So it's all work that's prevented up front before the code gets checked in from being a problem. It's not something we're retroactively having to go deal with. So a lot of people, whenever you start talking about Rust, they go, well, systems seem to boot, the world's running fine. Is memory safety really an issue? And the answer is yes. This is just an example of some of the issues that would be solved in a better way by writing it in a language like Rust. And these are some of the language features that we would use to solve that problem. So we're not depending on developers to get pointer arithmetic correct. We're using slice bounds, right? That automatically, whenever you're referencing the data, check to make sure that you're within the range that's allowed for that data. We're using dynamically sized structures so that we don't have to do complicated reallocation logic, and it plays right into our allocators that we've written in pure Rust. So this, I'm not going to go through every example. Part of this presentation is me sharing the information so that afterwards you have a place to go to look at some of this data and get the information to understand this problem better. And this is part of that in terms of the CVE side. So how does Rust actually help with all of this? We don't have a lot of time in this 30-minute presentation to go into the language itself. Fortunately, it's a very well-documented language, and the tooling is much better than C. So whenever you compile code and something goes wrong, it's going to suggest to you what you are doing wrong and how to work with your code to make it better. And so you'll work with the compiler a lot more. But I'll go through some of the key parts of the language that help you think about how to write code more safely rather than trust people that your code is working safely. So one of the main concepts of Rust is ownership. In Rust, each value can only have one owner. And if you think about that, it's important because you prevent use after free and double free and these types of problems, right? Only one person owns that value. Therefore, you are prevented by design from using that after it is no longer available because you don't own it. That person owned it, they went out of scope, it's dropped. And so ownership is one of those pieces of the language that's built in. And this is a simple example that I did on a Rust Playground, which is a website, to show how this works, right? Where you transfer ownership of this V to this V2. And now we no longer have ownership to be able to print that in the print statement anymore. So as a developer, I am prevented from making this mistake. It's not allowed. Now, whenever you go into that thing, you get into borrowing, right? So we have these things that we own, but sometimes you can't just always transfer ownership. You need to borrow it. And this is where a feature of the language called the borrow checker comes in. The borrow checker ensures that it checks the mutability of the data in terms of there only being one person that's allowed to reference that data with a mutable reference, and the rest are all shared references that are immutable. And what this ensures is that as I start to share a reference to this data out, that people are not able to have data race conditions, right? By language design, we cannot have two references that are immutable or that are mutable to the same data. It's not allowed. So it's not a problem. So that's another key feature of the language to look into as you go into this. But again, this is all about preventing problems up front. The final one that you get into, so if you own data and you can give references to data, you now have to make sure that data is valid for some period of time, right? You don't want to reference stale data. That's another common problem. So this is where we get into the lifetime feature of Rust and tracking what regions of code are valid for what period of time. And this is showing an example here where we've declared a variable X that lives in this scope. And whenever R tries to get a reference to X and use it outside that scope, it's not valid, right? That lifetime was within the scope of that block there. So those are just some quick examples, because I know whenever people hear about this, it's kind of hard to say, well, what does this actually look like to code? I can write C code really well. Does this really put any guardrails in place? Yes, it does. So then the other question is, how is this different than C, right? And the main thing to think about here is that these are compile time errors. They are not runtime errors. All of that you saw, those problems were caught at compilation time. So we're not checking in code that has bugs and waiting until runtime to find them, where we need to have a debugger and all that kind of stuff. We're finding them at compile time. The other key difference is, rather than being a really good C developer and hoping that things work out and know that this module is written by someone who's really good, so therefore I trust it, Rust has it built into the language that you can mark code as safe and unsafe, and all safe code has the memory safety guarantees. So whenever we look at a project like Patina, we're at about 12% unsafe code, and that's an entire core. We're not an application written on top of a C core. We are the allocator. We are the dispatcher, right? And so we've implemented all of this from the ground up with no C code, just all Rust. We're at about 12% unsafe code right now. And honestly, a lot of that is because we're writing an CFFI around the C interfaces to support compatibility with the current C UEFI APIs. But the nice thing about what this does is you can't call unsafe code from safe code. You have to use it in an unsafe block. And so you have those types of things built in and enforced there. So a lot of people, whenever they see unsafe, they say, well, how safe is all this code? Because fundamentally, you're just built on unsafe code. So is this really any better than C? The answer is yes, because unsafe code doesn't mean it's unsafe. It means that you're marking that code such that whenever you have to go back and find memory safety problems or audit the code, you now have a language enforced small subset of code to go look at. And it doesn't necessarily mean that the code can do whatever it wants. It's not like in the unsafe code, you can go off and everything about Rust goes away. What it means is that you can do these 5 things on the slide. You can dereference a raw pointer. You can call another unsafe function or method. You can access or modify a mutable static variable, and you can do these things with the traits in union. But that's it. That's what unsafe gives you. It gives you nothing else. It gives you the ability to do those. And so whenever we need to go and write a function to a CFFI, we'll mark that unsafe, right? Because we can't trust what's happening behind that. And if we need to dereference a raw pointer coming in, that's unsafe. But that's where we typically get into unsafe code. Then the question comes up, well, I work with a lot of data structures and I have to do pointer arithmetic to work with those structures. Isn't that all going to be unsafe? Because I'm used to writing pointer arithmetic. There are crates, like one's called the zero copy crate, that allows you to do that purely in safe code. And we've done that. And that code ensures that you're accessing the data structures correctly. So you can really minimize your amount of unsafe code. So whenever we started this work, there were a lot of challenges. This goes into how we chose what to initially work on. And part of this was, okay, well, if we do this work, do we really want to do the applications or do we want to go to the core and rewrite it ground up, right? And that's where we saw the most ROI in doing this work. The other piece was ensuring that we can actually sustainably build a UEFI platform code around this. And so we had to have a strategy of how do we take the most meaningful, probably subset of code that we can, which is the core, and how can we talk to other vendors and other people so that they can plug this into existing code and be able to work on top of it. So we're not asking everyone to become a Rust developer. We're asking them to use a safe core that they can run their code on top of. And so we've kind of inverted the model from safe applications running on an unsafe foundation to applications that are safe or unsafe running on a safe foundation. And so that was part of the original thought behind this approach. This is kind of going more into the 3 different areas we went to. So initially 2020, we think about applications. Then we go into, let's try to build Rust in the EDK2 build system, because that's where we build everything else. Can't we just have like Rust code get built in one build process? And we did that, and we do have that that code available. But what we found is that EDK2 code and Rust code are both opinionated about the way that you lay files out, and they just don't work well together. If you're trying to mix the two, you're not getting the best of both worlds. You're kind of like mixing things up there. And so we went with this project called Patina, which is a pure Rust DXE core that gets built as an EFI binary that you put into a platform. And that allows you to just take this EFI binary, drop it into an FDF or into your platform firmware and boot it up. This is all part of a new organization called the Open Device Partnership. This here is an organization that is focused on modernizing firmware development and system development. Part of this is writing services like embedded controller code in Rust. And of course, this is an example of UEFI code in Rust. You can go check out the website for more information about that. The Patina project itself is focused on modernizing UEFI. And so we are eliminating problematic features and patterns. There are some things that are allowed today in firmware, like a priori, traditional SML and stuff like that, that we just don't support. The other thing, going into the binarly presentation just beforehand, we require page aligned sections so that we can apply paging protections to those pages. And we have all of the memory mitigations turned on by default. We simply will not execute drivers that don't comply with that. We want to reuse more code from open source community and other projects. For example, our PE cough code is not written by us. That is an open source crate called Goblin. We use that code as is. We've contributed code to that project to handle some things like terse executable images that are specific to UEFI. We want to go from the 1% unit testing we're at today and get above 80% unit testing with Rust code. And we find that it's much easier to do that in Rust. It really is built into the language really well. And from the start, we're putting an emphasis on testing there. We work with the PI-based dispatcher. So we dispatch EFI images throughout the boot. So that means that you can take this Rust DXE Core, you can take 100 or 150 DXE drivers, and it dispatches them just like it does today with the C DXE Core. So notable features to go over really quick. We support ARM64 X64 architectures. We have Q35 SBSA firmware available. We have built-in decompression for Brotli and LZMA written in Rust. We, like I said, have eliminated some things like traditional SML that not necessarily Rust related, but as we talk about the overall modernization effort of firmware, we want to move the overall industry in the right direction, and getting rid of traditional SML is part of that. We have infrastructure for on-platform testing, the page table management I just mentioned. We have the ability to dispatch pure Rust code in addition to the PI code, so that we have two simultaneous dispatchers. Performance tracing support is there in terms of providing like the UEFI performance data. We've run SCT. Those are the results. We have a tool that will help report compatibility for the code as well that you can use. This is a quick overview of some of the requirements of things that we remove. So whenever I said we remove problematic features, this is kind of more specifically what I'm talking about. So traditional SML, we don't dispatch. Driver sections must be aligned to 4K so we can do the things that the binarly presentation was highlighting and apply NX protections and memory mitigations. We ensure that platform resources do not overlap. We enforce that we can do null pointer detection in page 0, and we check the caching attributes on MMIO and reserved resources. A lot of people today don't actually report their MMIO and reserved resources in a way that it's easy to map those into proper paging in DXE. This is covering at a high level what we've moved into Rust versus we haven't. I won't spend a lot of time here, but the green stuff is what's in Rust. And as you can see, a lot of the core is in Rust with these other services built on top that are a mix of some of these drivers, like the variable architectural stuff comes from runtime drivers, and we haven't moved the runtime code quite in yet. This is our initialization flow. We kind of start by processing hobs. We initialize the DXE code, and then we go into a dispatch of drivers there. Pretty similar to the C flow. We take hobs as input, but all of this is in Rust from the ground up in terms of the way that we dispatch. One of the reasons why we wrote the Rust core wrote the DXE core in Rust is because all of those services that I was talking about earlier, the boot services, come from the core. And so as we have these C drivers being dispatched and they're calling into these services, what we get is we can kind of multiply the effect of our safe code across the entire boot process by having those call into safe Rust code. And this is showing how many times some of those services get called on a typical platform boot in QEMU. One of the things that we have is a component model. And so if we think about the static compilation checks that Rust performs, it works a lot better in terms of tracking lifetimes and the validity of data if you do that as in a static compilation. And so we bring a lot of code into this one binary called the monolithic Patina DXE Core. And that binary kind of over time will bring in more and more C functionality such that we can remove those C drivers from the flash file. And this is kind of showing how we hook in the different components and things like that into that binary. In terms of our development process, we use RFCs for major changes. So this documents like major designs coming in. We use GitHub issues. We publish documentation through ILM-dbook. We use cargo release for publishing our code to crates. We use cargo LLVM for code coverage. We check for undefined behavior using a tool called Miri. So whenever you write unsafe code, you can run additional tools on top to actually check for undefined behavior in that code. And Miri is one of those tools that allows you to do that. We use cargo deny to do licensing checks all the way down the entire dependency graph. It checks all of our dependencies against the Rust security advisories, checks for redundant crates. We do crate vetting. So that's where people go and write. They vet to crates after they audit them. And we use crates from Google and Mozilla and other places as part of that. Unit tests work a lot better in Rust than in C by default. This is showing an example where, at least for firmware development, this is showing an example where we have it in the IDE where we can see test coverage in real time as we are writing the code. So you can look into that a little bit more if you're interested. This here is showing the Patina DXE Core on QEMU and how a platform integrates it. So whenever we provide the Rust code, we provide largely a set of libraries that you use as a platform to be able to configure a EFI binary the way that you want that will serve as your Rust DXE Core. And this is showing here how we do that for the QEMU platform. So it's bringing in the Patina DXE Core as a library crate. And then we are adding functionality on top as a platform. So you can kind of think of this as like your DSC almost, right? Where you're attaching different libraries, you're able to add different modules onto there. The other thing that we have is whenever we do things like write the core in Rust, we're able to easily patch this in for development. So a lot of people might think, well, if I write the code in Rust, is it slower from a developer cycle than writing it in C? Because now I'm having to do a separate compilation and bring that in. What we've done is build the EFI, the Rust code, which takes a few seconds generally with an incremental build. And then we patch that into the UEFI ROM, and we can run that within seconds. So we can make a change inside the Rust code, like the DXE Core. We can compile, we can run one command to compile, patch, and run that in QEMU. About 10 seconds later, we're actually seeing the code executing, and this is showing an example of that happening. All right, so next steps. We want to continue minimizing the use of unsafe code in Patina. So I said, like, there are tools you can run that count the amount of unsafe code in your files. We're, like I said, we're roughly at like 12 or 13%. We'd like to obviously continue to focus on minimizing that where we can. We want to bring more of these components into the Rust monolithic binary. So basically taking things that are C drivers today, and instead of relying on them going through that PI dispatcher, write them in Rust code and have them go through the Rust dispatcher in that monolithic binary. And that is kind of the main way that we see being able to scale this over time. People can take this today, make a platform work with it, but as we have interest and the ability to go and rewrite some drivers in Rust, we can do that and we can bring them into the monolithic binary. Specifications could be updated as well for some of this. A lot of things are written with C interfaces in mind, and we can work with those today, but there might be improvements in a few of those that could be made in order to work better with Rust. And then finally, collaborate on Patina with the community. So the reason we're here is to bring awareness about the issues today with memory safety and firmware, but also the different solutions that are available in terms of the Rust programming language, this project, how it is able to integrate into a platform to work for you today if you're using kind of PI-based firmware. and then also get feedback on these different pieces. So testing frameworks, organization and layout, the component model that we've introduced for pure Rust dispatch using dependency injection, and opportunities to share code. So even if you don't work necessarily in UEFI a lot, maybe you work in a place that like you're writing a networking crate, we can pull in here as well. So we could talk about that. That is everything.
Okay. Running a little behind, but we can make time for a few quick questions. Okay.
It's a great initiative. One question I have related to this is for, let's say, newer architecture. So where UEFI code already exists, it's much easier to port it to Rust and get it upstream, get reviews done, etc. For newer architecture, let's say RIS5, I'm still in process of developing standalone management mode. The question is, will I have to first upstream the code in C because my reviewers may not be like that expert looking at the Rust code and review it? Or is there probably that will be a challenge, right? I can't just go upstream my code in management mode and get it reviewed. So it will have to be like two-stage process. First, get it done in standard UEFI TNO core implementation, then bring it over.
Yeah, I think if you're writing something new, like what you're doing, and you want it to have maximum compatibility, you can do that. The other option is that you can actually just write it in Rust and compile that Rust code as its own EFI binary, and then people can use that as well. So you can take like your Rust code, compile it to an EFI binary, and then people can take that binary and use it in their platform like any other DXE driver. Right. Yeah, your reviewers will have to know Rust to review the code. The nice thing is, whenever you do Rust reviews, I will say you spend a lot of less time on what I would call. You realize how much time whenever you've done Rust code reviews and you go back to doing C code reviews, you realize how many things the compiler would have had the person fix before they got to the code review. And so the nice thing about Rust code reviews is it is less work generally than C code reviews in our experience.
Hi, you might not be able to answer this question. Microsoft obviously a big company. Are you working with any Silicon partners, steering them towards using this as the BIOS for the thing that you're developing together? When is the soonest we'll see this in big deployment?
Yeah, so we're kind of announcing this like today. This is the first time I think we've publicly, this is all open source, by the way. Everything that we're doing is in the ODP GitHub organization under the Patina repo. We have the complete like QEMU platform firmware code up and available. You can go build it and run it. We were actually talking about running the Go application from yesterday in QEMU with this as our core. And so then we'd have Go going into the Rust code. But we have had some of those discussions, but given that we're just bringing this out, they're still in progress in terms of, but it would be beneficial to everybody. I think everyone knows the value of getting something in the reference implementation because then it flows down that much easier.
Hey, so over here, I noticed you don't have runtime yet, and you don't have set variable or delete variable or anything like that. And you don't have SMM, so I'm wondering, is secure root actually enforced in any way at all yet? Or is that just going to be something that is just, you're not to it yet, or what?
So this is a full replacement for the DXE Core. We support everything, including secure boot.
So how are variables protected?
So they're protected by the C driver. So whenever you bring variables in, you have to essentially write your MM stack, because all that the variable DXE code is doing an SMI into the actual variable code written in MM. To run MM code, you have to have an MM core.
Okay.
And so one of our main next steps is to write an MM core in Rust.
All right, thank you.
And it's actually for that exact reason, because we do want to get that there.
Sorry, we are behind 5 minutes, so yeah, I'm sorry. So if you have any more questions, please contact Michael directly. After this, we'd like to get to the next one. Thank you. Thank you, Michael.